Okay, pre-AP chemistry. I'm going to teach quantum numbers and electron configuration. And so we're going to learn how to do the electron configuration. I should have already talked to you once about this, and I'm making this YouTube video just to help explain everything a second time with some color coding and things like that. But the first thing that we're going to do is start out with our first quantum number. There's 4 total quantum numbers, and they help us write electron configurations. So the first quantum number is our principal quantum number, and that number is going to tell us our energy levels. And so that one's always telling us what energy level we are in. And our energy level is pretty much our row. There's a couple of exceptions, but we have 7 rows on the periodic table, and we have 7 energy levels. So this first row is your first energy level. The second row is your second energy level, third row, fourth, fifth, sixth, seventh, for our energy levels. And if you go down here, this is 6th and 7th because they're inserted right here. So we have our 7 energy levels on our 7 rows. D's and F's are exceptions because we'll have to subtract because they're on a different energy level. But we'll get there in a little bit. I don't want to get too ahead of ourselves. So the first quantum number is your principal quantum number, and it represents your energy level. Every time we write an electron configuration, for each electron, we need to say where it's located as far as its energy level goes. So each time you do one, you're always going to have a big number to start with that represents your energy level. And I'll show you an example of that in just a minute. And then our second one is our angular momentum quantum number. And this one is telling us the shape of our orbital. So we know that electrons orbit around the atom, and they orbit in a certain shape, in a certain direction. And so whenever you think about the planets, they rotate and they orbit in a certain shape. And the same concept goes for your electrons, but the shapes that they orbit in are not the same as our planetary system, to where it's all the same. It's those oval like rings. It's not that. They rotate in different types of shapes. And so we actually have a sphere and a dumbbell. Those are the 2 that we're concerned with. But we'll learn about those. But how we represent the shapes when we're writing electron configuration is by letters. And so we have S, P, D, and F. Those are our letters, and they represent the different shapes, the different types of orbitals. So our first one's our energy level, and it's just going to be a number 1 through 7. Our second one is a letter, and it's going to be S, P, D, or F, and it's telling us the shape. Then our third one is called our magnetic quantum number. And then this one is indicating the orientation of the orbital. So whenever we're talking about orientation, and I have a representation of this, and we have different, so if you think about orientation, we're talking about like an X, Y, and Z axis for the P's. And so how that looks, my S orbital is sphere shaped. And so the sphere shaped one, and this isn't a perfect sphere, but let's pretend like it is. So no matter how I rotate it, it's the same on this axis, that it looks the same the whole way through. So it doesn't matter if, like here, just so you can see that I'm rotating it, if I go this way, it still looks the same as it is this way. And so it doesn't matter. So there's only one orientation for an S, but for a P, I could rotate it and it would look different. So whenever I rotate it like this, it looks one way, and then if I rotate like this, it looks different versus this. And so this one has 3 different orientation types. And how that works, I have 3 different sets of balloons, and we can put them all together, and you can see how they all can coexist at the same time without interfering with each other. Almost got it. I just need these 2 to flip-flop, and then we'll be good. Balloons. Okay, there we go. So as you can see, all 3 sets are existing. So I have like my Y, my X, and my Z, and they're all existing. So it has 3 different types of orientations. So that next number is not one that we necessarily represent physically when we write an electron configuration, but it does change how many electrons we can have, because it changes how many different types of ways that the orbit of the how many of the different orbitals can fit in there. So that being said, we have the different orientations. And so S's only have 1 orientation, which I just showed you. P's have 3, which I just showed you. D's have 5, and F's have 7. So you're pretty much going up by odd numbers. So it's pretty straightforward to remember. But that being said, each orbital can hold a max of 2 electrons. So this s orbital can only hold a max of 2. It could have 0, 1, or 2 in it. So if you think about it like a shoebox, your shoebox, if you're wearing both your shoes, has 0 shoes in it. As you're taking them off or putting them on, it might only have 1. And then as you put them away, it can have 2, but it can't fit more than 2 in there. If you try to put more than 2, they don't close all the way. So same thing with your orbital. It can have 0, 1, or 2 electrons in there, but max of 2. And so for the S's, each time we can only have 1 per energy level, or 1 set per energy level, so that's 2 electrons total. The P's, so this is 1 P, so in total 2 electrons can fit in here, 0, 1, or 2. And that's for the whole thing. I know it looks like maybe 2 could go here and 2 could go here. It's 2 for the entire thing. And so that set I just showed you can hold a maximum of 6 electrons because 3 P's can exist at a time. So D's can hold 10 because 5 D's can exist at a time, and F's can hold 14 because 7 can exist at a time. And so this will hopefully make more sense as we go through, but just to get the basics. And then the very last number is our spin quantum number, number 4. And our spin quantum number is telling us the rotation of the electrons because the electrons are spinning. And so what we like to say is they spin in opposite directions. So they're going to repel each other because 2 like things don't like each other. And so those 2 negatively charged, when they come close to each other in that orbital, so in your S, your P, your D, or your F, in your shoebox, when they come close to each other, they go yuck, and then they start to spin away from each other. And so we know one spinning clockwise and one spinning counterclockwise. And so they spin in opposite direction. So that's our 4 numbers. First one is our energy level. It's called our principal quantum number. Our second one is our angular momentum quantum number, and it is our shape of our orbital, S, P, D, or F. Third one is our magnetic quantum number, and it is going to be our orientations. And so S's only have 1 orientation, P's have 3, D's have 5, F's have 7. And then the last one is the spin quantum number, and it's just telling us if they spin clockwise or counterclockwise. And we represent clockwise with an up arrow and counterclockwise with a down arrow. And so we'll do all of those in an electron configuration. And so right now I'm going to show you one simple electron configuration before I end this video. And I'm going to do it for oxygen. So oxygen is right here. So we have to account for all of the electrons that oxygen has, and it has 8 electrons because remember, atoms are electrically neutral. So it's 8. We're going to start in that first energy level and work our way through because electrons are always going to fill the lowest energy level possible. And so what I say is just start at the periodic table. So if we just start where we know, and I'll just do it on this one, and then I'll show you the one behind me later. So first I'm going to say my energy level. So I'm in row 1, that's energy level 1, so I'm going to put a 1. And remember, this is for oxygen. And then my shape. So if you look behind me, I have the periodic table tells us our shapes. And so this first section, this whole section is an S. This whole section is P, D, and F. And helium is also an S. And so that means that hydrogen, where that first electron would be, is going to be in the S orbital. Okay? And so then one of those is going to be, remember our S can hold up to 2. One is going to be in that hydrogen. But guess what? There's a second 1s, and so we're going to have 2 total. So this guy's full, so now I got to keep going to the next energy level, which is the second energy level, because now I'm on row 2, so I went from hydrogen to helium. Now I'm on lithium. Second energy level, so I put a big 2. I'm in the S's again. Lithium is still in my S's, so I'm going to put an S. I'm going to count through. Lithium and beryllium, they're both in the second energy level and in the S orbital. So I'm going to put a 2. And then I'm going to keep going. Now I'm over here, still in row 2. So I need to remind everybody that this is energy level 2. Now I'm in the P section. And I'm going to count over 1, 2, 3, 4. 1, 2, 3, 4. So I'm going to have P, 4. And this is the electron configuration for oxygen. So remember, we start at the top. So I did my 1s1. I'll get up closer actually. 1s1. 1s2, 2s2, because I have 2 of them right there, 2p, 1, 2, 3, 4, and I stop at oxygen because that's what I'm looking for. And I'm at my max amount of time, so I'll do another one in a second.